Hi everybody, welcome to another in my series of videos on computer systems. In this video, we'll get started with Module 4, where we'll be talking about memory allocation. This is coming, for those of you following along in the textbook, this is coming from Computer Systems, a Programmer's Perspective, and this is actually Chapter 9, Section 9, so we're just looking at one section in this module, and we'll be talking about how dynamic memory allocators like malloc work. So what's dynamic memory allocation for? Well, programmers use it to acquire virtual memory at runtime, and this is where we'll use stuff like malloc and free. And this is for data structures whose size is only known at runtime. Right? If I'm not going to know the size of a data structure until the program is running, I can't just allocate a certain amount of space on the stack or something for it, right? I have to have some kind of dynamic memory storage assigned to my process that gets managed by this dynamic memory allocator, and that space, okay, that's part of the process virtual memory. So each process has its own stack. It also has its own heap, and that's what that area of memory is referred to. It's called the heap. Now notice in this illustration over here, the heap and the stack are kind of growing toward each other. Remember that our stack grows downwards in memory. Our heap actually grows up, and so they're growing toward each other. The top of the heap grows toward the top of the stack and vice versa. Now, we notice that there's this thing called a BRK pointer, that's the break pointer, that gives us the top of the heap. That's the space that's allocated for the heap, and we can use another thing called SBRK, right, to set an increment that we're going to increment that break by. So I can actually grow my heap if I want to. And when we call SBRK, what we're going to get returned by that is it's going to grow the heap by some increment of bytes, and it's going to return the previous break pointer. So that kind of gives us a pointer to the bottom of the space that we just allocated toward the heap when we use that. So that's all we're talking about. Is this heap is just something where we can kind of play with, where we can put data structures when we don't know what their size is necessarily going to be before the program runs. So let's talk about a few terms. Now, an allocator maintains the heap as a collection of variable-sized blocks that are either allocated or free. So you could have blocks that are 1 word, you can have blocks that are 100 words, you can have variable-sized blocks, and they're either going to be allocated, right? So they're being used for something if they're allocated, or they're free, which means that, okay, we could allocate them, we could put something into these free blocks. Now, we've got a couple different types of allocators that we're going to want to talk about. We have explicit allocators, and that's an application that allocates in free space, so looking at malloc and free in C. Or we have an implicit allocator, and that's an application that allocates but doesn't free space, so like garbage collection in Java or Lisp. And we'll discuss simple explicit memory allocation today. Let's start with the basics, and we'll take a look at explicit allocators in Module 4. So let's refresh ourselves on malloc, or introduce you to it if you haven't kind of looked into this before. And we've got two main functions that we use with malloc. We have the actual malloc function where we give it a size. And what malloc does for us is just allocates a block of memory. It's going to return a pointer to a memory block that's at least size bytes big. And typically, remember our video on memory alignments, right? It's typically going to be aligned to an 8-byte boundary. Now, if we give it a size of 0, it's just going to return a null. Okay, and if it's unsuccessful, right, so that's what happens with a successful call. If we try to call malloc and the call is unsuccessful, it's going to return null and set error number, right? It's going to indicate that something went wrong using the ERRNO header. Now, When we free, all we're going to do is give it a pointer to a block pointed at, to a block of allocated memory, and return that block to the pool of available memory, right? So we're going to give it the address of an allocated block and say, hey, this shouldn't be allocated anymore. This is free again. And something to keep in mind, though, is P has to come from a previous call to malloc or realloc. We can't just give it an arbitrary pointer. We have to give it a pointer that we got from an allocation call. Okay, so we can't just go around willy-nilly freeing whatever memory we want to free, whatever pointer into, some area of memory that we want to free. We can only pass it a pointer that comes from a previous allocation call. Now we've got some other functions to be aware of. All right, we've got calloc, which is a version of malloc that initializes the allocated block to all zeros, right? So just plain malloc, we're just going to get the pointer. It's not going to do anything. So there might still be some stuff left over there from previous allocations or previous things that were going on. We might just have kind of gobbledygook in that memory location, in that block of memory. There might be data sitting there. Right? It just doesn't actually mean anything. With calloc, we can actually initialize all of that to 0 and zero that all out. Realloc changes the size of a previously allocated block. Right? So if I allocated 8 words previously, I could use realloc to change the size of that block to 16 words, for example. And then sbrk, which we mentioned on the last slide, that's used internally by allocators to grow or shrink the heap. So for the most part, you're not going to have to deal with that directly, but we want to be aware that it's there. And you could actually use sbrk to just get the address, to just get a pointer to the current break pointer, because we could actually call that with a 0, right? We can call sbrk and grow the heap by 0 bytes. And remember, when we call sbrk, it returns the pointer to the previous break pointer. Well, the previous break pointer, if we called sbrk with 0 bytes, would be the same as the current break pointer because we haven't actually changed it, but we're going to get that pointer back. So we can use that in a couple different ways, right? We can actually grow the heap with it. If we pass in a negative value, we could actually shrink the heap, or we could pass in 0 and just get the current break pointer if we wanted to. So let's talk about some assumptions that we'll make in these video. Memory is word addressed. Okay, each word can hold a pointer, and we're going to address memory as blocks of words, and we'll have the allocated blocks shaded in with green or some other color, and the free blocks will just be in white. They'll be unshaded. So in this example here, we have just sort of an indication of here's some portion of memory. Each individual square is going to represent a word, and this block of green shaded words is just an allocated block that's 4 words long, and this one that's white squares is a free block that's 3 words long. So let's just make sure we understand how these diagrams are going to work, because we'll be using these throughout the video, and we want to make sure we understand what we're looking at. So let's take a look at how we'd use these diagrams to show a series of allocation and free calls. So for our first line up at the top here, we call malloc 4, right? So we give it a size of 4 words, and we assign that to just P1, right? So that's just our first pointer pointing to some allocated space. And we see in the diagram we have 4 words shaded in yellow to indicate that that's allocated and the rest is free. Our next call is malloc 5, so we allocate 5 more blocks, and we're doing this sort of in a first found kind of way here, where we just pack the allocations close to each other. So we just go to the first free block and allocate as we can. So we've now have that P1, which is allocated, that 4 words, and we have another one, P2, which points to an allocated block of size 5 words. For P3, we malloc 6, so now we add another allocation of 6. Now our fourth call here, we're actually going to free P2. Okay, so we have that pointer to P2, so that tells us what we're going to free. So we're going to free the block pointed to by P2, so now that's white blocks to indicate we no longer have that allocated. And that means that when we call the last one here, when we malloc 2 and assign the return to pointer P4, we can actually put that into our newly freed space. So now we've got our P1 followed by P4, then a little more free space, and then P3, that 6-word block. So now that we've talked a little bit about the basics of how these things work, let's talk about some constraints, right? As with anything, we have some rules that we have to follow when we use these things. So applications can issue an arbitrary sequence of malloc and free requests, and each free request, remember, has to be to a malloc block. We can't just free whatever address we want to. We have to give free the pointer to a block of memory that we've allocated using malloc or realloc. Now, the allocators themselves cannot control the number or size of allocated blocks, right? They're just going to do what they're told to do by the application that calls them. They have to respond immediately to malloc requests, right? You can't buffer these requests. I can't just stick it in a queue and, wait for a certain amount of time. I've got to do this right away. We have to allocate blocks from free memory, right? I cannot go I can't go replacing allocated memory. I can only allocate from free memory. I have to align blocks so they satisfy any alignment requirements, right? So for GNU malloc or libc malloc on Linux boxes, it's going to be an 8-byte alignment. But basically, whatever the system and compiler alignment restrictions are, malloc and free have to follow those. We can manipulate and modify only free memory, right? Remember, we can't, compact things. I can't move allocated blocks around. I really only get to mess with free memory apart from those calls to free where I actually take an allocated block and free it. I can only allocate things into memory that's already free. And again, can't move the allocated blocks once they're malloc, right? So again, compaction is not going to be allowed. The next thing we should probably talk about are performance goals. Now, as with anything in a system, we want to meet certain performance requirements. We want to increase our performance as much as possible. So let's take a look at 2 performance goals that we deal with when we're talking about memory management. The first is throughput. Now, that just means given some sequence of malloc and free requests, right? R sub 0, R sub 1, all the way up to R sub n minus 1. These are just individual requests to malloc and or free, doesn't matter. We want to maximize our throughput and something that we'll talk about on the next slide, peak memory utilization. And these are often conflicting goals. Now, throughput is just the number of completed requests per unit time. So if I've got 5,000 malloc calls and 5,000 free calls in 10 seconds, then my throughput is 1,000 operations per second, right? I've got a total of 10,000 operations that happen in 10 seconds. That means I'm completing 1,000 operations per second. That's my throughput. So that's pretty straightforward, right? It's just the rate at which we can process our requests to malloc and free. So let's move on to that peak memory utilization. Now, this one, there's a little more math, but not much. So given that same sequence of malloc and free requests, we're going to have a few different definitions that we want to keep in mind. We've got our aggregate payload, okay? That's P sub k. Now, every malloc call results in a block with a payload of P bytes. All right, so after a request R sub k has completed, the aggregate payload P sub k is just the sum of the currently allocated payloads. All right, so we're just going to take all of the requests that we've done so far, all of the allocated blocks, add up their payloads. That's our aggregate payload as of that particular request. We also have to deal with the current heap size, right? So H sub k. We assume that H sub k is monotonically non-decreasing, right? So the heap only grows when the allocator uses SBRK, okay? But that just means the heap size at request K, or as of the time that request K was made. So our peak memory utilization after K requests is just going to be, or we'll refer to it as U sub K, right? Utilization after request K. Now that's going to be the maximum payload, okay, up to request K divided by the heap size. So what's the most amount of payload that we've used with respect to the heap size throughout this selection of requests. That's our peak memory utilization. It basically means how efficiently are we using the heap. That gives us an idea of what that peak memory utilization is. And we want that, of course, to be as close to 1 as possible. We want to make sure that we're not allocating a ton of extra space, a ton of space that we don't actually need for that heap. So what can cause us problems with that memory utilization? And so, something that's a big culprit of that is something called fragmentation. We have both internal fragmentation and external fragmentation, so let's talk about what those are. Now, the good news is that these are both fairly straightforward, so we'll just take them one at a time. Now, internal fragmentation. For a given block, internal fragmentation occurs if the payload is smaller than the block size. And so if I've allocated a big old block, but I'm only actually using half of it for the payload, I've got internal fragmentation. Now, this can be caused by the overhead of maintaining heap structures. It can result from padding from alignment purposes. Remember, in previous videos, we talked about how structs are set up and how we might have to have allocated but unused bytes, right? So that's internal fragmentation right there. And we could also have explicit policy decisions. We might actually choose, for various reasons, to return a big block to satisfy small requests. That's going to give us internal fragmentation as well. Now, this one's easy to measure, right? It's only dependent on the pattern of previous requests, right? We're dealing with blocks that we've allocated and dropped a payload into, so we know what's happened, so we can figure out what our internal fragmentation is. Now, in the case of external fragmentation, this is where we have enough aggregate heap memory, but we don't have a single free block that's large enough for the call we want to make. And that because of that, we'd have to end up using that SBRK. We'd have to grow our heap, even if we already actually have enough free blocks or free words to satisfy the request. It's just organized wrong, right? We just don't have enough of a contiguous number of words to get this latest block. So in this example, we take a look at the same series of things that we did in the first example where we saw these diagrams. We malloc 4, we malloc 5, so that just gets packed right on there. We malloc 6, everything's fine so far. Then we free P2, so we free that block of 5. Now, in the first time we went through this example, our last call to malloc was just for 2, so that wasn't a problem. We could just drop that right in after P1, after that 4 blocks from that first call. But what if we had to allocate a 6-word block? Well, oops, we don't have 6 blocks in a row, so that's a problem. We would now have to grow our heap to fit that new allocation in. That's what we're talking about when we say external fragmentation. And this one is really tough to measure because it depends on the pattern of future requests. So when I'm sitting there having just made that call to free, right, I've just freed P2, I don't actually know what the next call to malloc is going to be, right? It could cause us a problem and it might not, right? I might call malloc 5, which I could just drop right in and I wouldn't have a problem. So again, this has to do with a pattern of future requests. So that one's kind of tough to deal with. So we have to basically come up with some general policy ideas to try to minimize the potential for that. So now that we know how we need this stuff to work, it leads us to some implementation issues, right? We have some questions that we have to figure out how to answer to make this whole thing actually work in the real world. So for one example, how do we know how much memory to free if we just have a pointer? Remember, a call to malloc just returns a pointer. So I know the address that this block starts at, but it doesn't actually return a size. You know, I give it a size when I call it, but I don't actually specify a size when I call free. I just give free the pointer to the address that this block starts at. So how in the world do we know how much memory to free if I only have, the address that this block starts at? How do I keep track of the free blocks? Especially as I use this thing more and more and I'm allocating and freeing all over the place. How do I keep track of what's free and what's not? What do we do with the extra space when we're allocating a structure that's smaller than the free block it's placed in? Okay, so if I've got a free block that's 10 words, and I only need a structure that I have a structure that only requires 8, what do I do with that extra stuff? How do we pick a block to use for an allocation? Right, there might be a whole bunch of different free blocks out there that would fit this thing that I'm trying to allocate for. How do I decide which free block I'm actually going to use? And how do I reinsert a free block into that? However, we're keeping track of the free blocks. Once I allocate a block, right, that's not going to be in our list of free blocks anymore. When I eventually free that block, how do I reinsert that into my collection of free blocks? So let's keep these questions in mind as we watch the rest of this and the next video, actually, because we're basically going to be answering that question. We're going to give you answers to those questions, and we're going to cover a bunch of different ways to do these things. Okay, and that's how we're going to get an understanding of how these dynamic memory allocators work. So let's start by talking about knowing how much to free. One standard method is to keep the length of a block in the word preceding the block. Okay, that's often referred to as the header field or just the header. But we want to keep in mind that requires an extra word for every allocated block. So when I make a call to malloc and I give it a size of 4, right, I'm going to have 4 words of data. There's my payload. I'll still return the pointer that's at the beginning of the data itself, but the block will actually allocate with the preceding word as well, right? And that's where we're going to store my block size. And I'll just make the block size 5 because I've allocated 4, right? But I've allocated 4 words for data, but the block is actually 5 words because I'm adding that extra header field to keep track of the size of the block. Now, this ties back to that internal fragmentation we talked about, right? Because I've got 4 words of payload, but I've allocated 5 words because I have to have a little bit of information to kind of maintain my sizes, and this is just extra sort of administrative information that I'm going to use to be able to allocate and free things moving forward. So we're going to cause ourselves a bit of internal fragmentation here because we're adding some extra information. We're not just dealing with the payload. We've got to use an extra word to keep track of things. Now, when we talk about keeping track of those free blocks, we've actually got several options. So in this video, let's talk about method 1, and that's called an implicit list. We'll actually talk about methods 2 and 3 in the next video in this module. So with an implicit list, we just have to keep track of the size and the allocation status. All right, we need to know whether it's allocated or free. We need to know how big the block is. And we should keep track of whether this is allocated, right? Am I using actual information here? Do I have payload? Or is it free? Can I use this for a malloc call? Now, I could store that in 2 words, but that would be wasteful, wouldn't it? I mean, allocated or free, this is a flag. Yeah, there's only 2 options. It's allocated or it's not allocated. So I only need a bit. Right? I can use 1 single bit as a flag to figure out what the status is. So where can I find a bit that I could use for that? Well, the neat thing is we've got blocks are going to be aligned, right? We've talked about how normally it's going to be like an 8-byte alignment. And we know some things about binary now. So we know that if a binary number is even, it's always going to end with a 0, right? If it's divisible by 2, it'll end with a 0. If it's divisible by 4, it ends with 0, 0. If it's divisible by 8, and that's the one that we usually think in terms of when we're talking about block sizes, it's going to end with 3 zeros. My least significant bits will always be 0, 0, 0 for a value that's divisible by 8. So I'm always going to have some zeros down at the low order bits. So instead of storing an always 0 bit, right, instead of just leaving those as always being all zeros and wasting a word on a flag, let's just use the least significant bit of my size as my flag. And then when I read the actual size, I just have to mask out that bit, right? So I can look at the bit to figure out, oh, is this allocated or is it not allocated? Then I can just mask that out and read the size of the block. So I can kind of use that little trick there to pack a little more information into that single word that we're going to allocate to keep track of things. So my block would have a size and an allocation status, right? And if A is 1, it's allocated. If it's 0, it's free. And A, again, that's just going to be my least significant bit in that word where I'm storing the size. The size is, of course, going to be the size of the entire block, and that will include the first word, that extra word that has my size, my header. It'll include the payload and any optional padding that I might have to keep my alignment proper. So let's take a look at a quick example of this. We've got this diagram here that can show you how we can just kind of walk down an implicit free list to go from block to block to block and check on the status, whether it's allocated or free, and we're going to use that header information, the sizes, to figure out where the next block begins. So we're assuming in this diagram, we're going to assume a 32-bit word size, okay? And we're going to say 8-byte alignment, right? So we're going to have double word alignment, right? And again, you can review those from the previous video where we talked about memory alignment. But we've just got these little dotted lines down at the bottom to indicate where our double word alignments are going to live, right? And so basically we just have to start everything on one of those double word alignments. Our first block here, we have 8 bytes, right? So that's 2 words. And after the slash here, we have a little 0. That just indicates that my least significant bit in that header, right, where we indicate the size, is going to be 0, indicating that this is a free block. So the total block size is 8 bytes. That's 2 words. We've only got 1 word that's actually free. We've got the first word that's the header. So the free block area starts at that double word alignment. The previous one here, the first word in that block, is that extra word that we've put in as our header. So we start there. Well, where's the next block? Oh, it's 8 away, right? So we hop over those 2 words and hey, we're on the header of the next block. That one has a length of 16 and there's 4 words in that box. So that's 16 bytes. And in this case, we indicate that the block size is 16. We have a 1, though, in that least significant bit, so this is allocated, and this one actually shows a little bit of padding there as well. All right, so we've got the header, we've got a couple words worth of payload, and we've got some padding. Our next block, again, if we start at that header and we jump 16, we jump 4 words ahead, hey, we're at the header of another block. This one is 32. If we count this up, we've got 8 words. Each word is 4 bytes. So, hey, there we go. We've got our 32 bytes there for our block size. And of course, the least significant bit is 0. So that tells me that this is a free block. And we just keep on doing that, right? We can just start at the first header we have. So all we have to do is keep track of where the first header is. Where's the first header in my heap? And then I can go to that and just hop, skip, and jump my way through the heap, checking each block to find out the block size and whether it's allocated or not. As we hop, skip, and jump our way through our allocated and free blocks, of course, we're going to find our free blocks, right? I mean, we're going through every block, whether it's allocated or free. So, I mean, eventually we're going to run into some free blocks. Now, which one to use, all right? So if I've got an malloc call, I've got to go find a free block. I have several different policies that I can use to determine which free block I'm going to use to satisfy this latest call to a memory allocation function. So I could do first fit, or I'm going to search the list from the beginning and just choose the first free block that fits. Okay, that can take linear time in the total number of blocks, both allocated and free, right? Because I'm just going to go until I find the very first free block that will actually fit this allocation call. That's what I'll use, and then I'll stop. I can also use next fit, which is like first fit, but you search the list starting where the previous search finished. In a lot of cases, that's going to be faster than first fit because it avoids rescanning unhelpful blocks. But some research suggests that the fragmentation is worst. So the difference between first fit and next fit is, I guess for the first one you called, you would effectively do a first fit because you're starting right at the first block. But you keep track of where you are in the heap, and then you start your next search at that spot where you ended your first search. So you just keep on moving your way through the heap like that, and then eventually wrap around, of course. You also have best fit. Now, this one, you search the list and you choose the best free block. Okay, so the best block means the one where you can fit your allocation call in, right? It's got to be big enough to actually work for the allocation call, but you pick the one that has the fewest bytes left over. So this is usually going to help fragmentation, right? Because I'm going through and I'm intentionally making sure that I don't waste space, right? I'm intentionally making sure that I use the smallest free block that will actually satisfy the allocation call. But this is typically going to run slower because I've got to search the whole thing. With a first fit, I might have to go hop, skipping, and jumping my way through the whole heap, but I might not, right? It might be the second thing I get to that ends up being my first fit. So in a lot of cases, that can run pretty quick, whereas with the best fit, I've got to scan that whole heap every time. Now, what happens if we want to take a big free block and make it into a couple smaller free blocks? Right? This is something called splitting. Right? And we might want to do this because allocated space might be smaller than the free space in the block. So I could split that block and make another free block out of what's left over so that I can decrease my internal fragmentation. Right? So I could add a block. Let's say I'm doing a next fit and I'm sitting at the 4 that's allocated, right? The block of size 4 that's allocated here. The next thing I find is this free block that's 6 words long. I could split that into a 4-word block and a 2-word block and just update my sizes and my allocation flags, and that'll just add that extra block in there. So I've gone ahead, I've split this block that's longer than I need it to be into 2 shorter blocks so that I can pack the data in a little more efficiently. But here's the thing, when I do this, splitting, or even if I don't split blocks, even if I just end up with free blocks next to each other, my simplest implementation to free a block is just clearing the allocated flag, right? I mean, that one least significant bit is how I determine whether this thing is allocated or whether it's free. But doing that can lead to something called false fragmentation. So what about this example? I've got a couple allocated blocks. I've got four words allocated here. I've got another 4 words allocated here. Now, when I free P, I'm going to have my 4 allocated words. I'm going to have 4 free words followed by 2 free words. But guess what? The headers still say that this is 4 and this is 2. So these are not, we don't understand that these are just one contiguous block of space. As far as our current method of doing things is concerned, that's a free block of 4 words and a free block of 2 words. And when I try to malloc 5, I can go from free 4-word block to free 2-word block, but the allocator won't be able to realize that, it's okay. This is actually 6 words of free space. It's going to see 4 words of free space followed by 2 words of free space. Neither one of those will fit a malloc call with a size of 5. So what do we do about this? Well, we can use something called coalescing. So we will coalesce or just join with the next or previous blocks if they're free. So if I'm looking at a free block and the next block is free or the previous block is free, I can just join them up. Now, this is pretty easy to do if we're talking about coalescing with the next block, right? So I free this block that P is pointing to. And so instead of having a free block of 4 followed by a free block of 2, I'll just change that. I'll find hey, is the next block free? Why, yes, it is. And it's a size 2. So I just add that to the 4. So I know I'll have one bigger free block that's size 6, and I don't even have to change the header from that block that was size 2 before. Logically, it's gone, because remember, with the implicit free list, we jump from header to header. So, that would just be garbage data that's in that free block that'll get replaced when we allocate it. But the question is, how do we do it with the previous block? Because the way we have things set up right now for our implicit list, my header tells me the size of the block, and it tells me, whether it's allocated or free, but it doesn't tell me anything about the size of the previous block. And since the previous block, it's just a word, right, that indicates the size, I can't even go, word by word back and find the next header. I have no way of knowing whether I'm looking at a header or whether I'm just looking at data that's part of a payload by looking at an individual word. So what do? How do I figure out what's going on with previous blocks? Well, we introduce a concept known as boundary tags. And really, we're just going to expand the idea of our header, and we're going to put a footer in as well for each block. So instead of just using one extra word as a header to indicate the size and allocation status, we'll add 2 words, one at the beginning and one at the end. And those will have exactly the same information, right? Both will indicate the size and the status of whether it's allocated or free, but we'll have it on either side of the block. Now, yeah, that means we're going to use 2 words instead of just one for sort of this, information that we need to keep track of things. But it allows us to traverse the list backwards, and that's a really, really helpful thing. So this is an important technique. It's a general technique. You're going to see this a lot in implicit lists. So again, we just keep track of it both at the header and at the footer. And the nice thing about that is, if I'm at a header, right, if my focus is on the header, I'm going to know the size of my block, and I'm going to know that, well, I'm using boundary tags, so I can actually jump to the footer and start traversing backwards, jump up to the next header and start traversing forward. So I can go back and forth in my list now, and that gives me a lot of options as far as helping me out with the coalescing and things like that. Now, what this does for us is it allows us to do this coalescing in 4 different cases that we see here, and we can do this in constant time. So for each case, we'll have the block being freed, and that's going to be surrounded by 2 allocated blocks, an allocated block before it and a free one after it, a free block before it and an allocated one after it, or whether, case 4 is where it's surrounded by 2 free blocks. And we'll take a look at each of these cases and see exactly how we go about coalescing in all of them. So case 1 is about as straightforward as it gets, right? We've got each of our blocks. Now, we have boundary tags on the top allocated block that indicate the size and the allocation status. Now, this block that we're going to free has a size of n, and it's allocated, so the flags show that. And then this next allocated block has the boundary tags indicating its size, m2, and that they're allocated. Now, since we're just freeing one block that's in the middle here, it's surrounded by allocated blocks, there's no coalescing to do. So all we have to do is set those least significant bits on the boundary tags to 0 to indicate that this is now a free block, and we leave the rest of the boundary tags alone. We don't have to change any sizes. Now for case 2, we have an allocated block followed by the block that we're going to free, so it's currently allocated, and then we have a free block after that. We know that the size of the block we're freeing is n. We know that the size of the block that follows it that's already free is m2. So all we have to actually change are 2 of our boundary tags. Right, we can leave the ones in the middle here alone because they're just going to be part of a larger free block. That'll get overwritten when we allocate. So we just have to add up the size of these 2 free blocks. So the sizes in the new boundary tags will indicate that the size of the total free block is n plus m2. And we set the least significant bits on. Really, we only have to change the one at the top, the header tag. We set that to 0. The one at the bottom is already 0, but we'll generate a whole new word, of course, for this. And we're just going to indicate that the size of the new free block is n plus m2, and that the least significant bit will be 0 to indicate that it's a free block. Now, when there's a free block before the block we free, it works pretty much the same way, right? We do exactly the same thing. We're just going to add up the sizes of the two free blocks that end up next to each other. In this case, we'll have one free block that's size n plus m1, and we have the least significant bits set to 0 to indicate that this is not allocated. Once again, we leave the boundary tags in the middle alone. We don't have to change anything there because they're just going to be inside that free space. And we're done, right? It's very, very similar to case 2. And finally, with case 4, well, this works again pretty much exactly the same way. We leave all the different boundary tags that are in the middle alone because we're freeing a block that's between two free blocks. So we just add up the sizes of all the free space that's now next to each other. So that's M1, the size of the free block that was before the block that we're freeing now, N, which is the size of the block we just freed, and M2, which is the free block that was right after the block we just freed. So our total size is N plus M1 plus M2, and we leave those least significant bits as 0 to indicate that this is just one big free block. So that's about everything we want to cover in this particular video. We want to be aware of placement policies, right? That's when we talked about first fit, next fit, best fit. Trades off lower throughput for less fragmentation. And one interesting observation about segregated free lists, which we'll cover in the next video, these can approximate a best fit placement policy without actually having to search the entire free list. So that's a handy thing to know, and we'll get into why that works in the next video. We've got splitting policy that we have to make decisions about. When do we go ahead and split free blocks, and how much internal fragmentation are we willing to tolerate in order to improve our utilization? We have to figure out coalescing policy. Do we do immediate coalescing, where every time free is called, we check to see if we can coalesce? Or do we do something called deferred coalescing, where we try to improve performance of free by deferring coalescing until it's needed? So we can coalesce as we scan the free list for a malloc call, or we can coalesce when the amount of external fragmentation reaches some kind of threshold. Or again, if we want to do it immediately, just every time we call free, I'll free the block, I'll check the previous block, I'll check the next block, and if one or both of those is free, I can coalesce right then and there. So again, these actually all have implications as far as your performance goes, so we want to be kind of careful about how we decide on these policies. Now, what we should take away as far as implicit lists specifically is that it's a very simple implementation, right? I mean, this thing is about as straightforward as it gets. The cost of allocation is a worst case linear time, right? If I just have to trip through every single block, then it's going to get linear time as our worst case. Our free cost is actually a constant time worst case, even if we coalesce, right? We're not, when we free, we're not dealing with anything that's dependent on the number of blocks we have, right? We're always just dealing with 1, 2, or 3 blocks, no matter what we're doing, even if we're coalescing. Memory usage is going to depend on the placement policy. Again, that's that first fit, next fit, or best fit. Now, this is not used in practice for malloc and free because of that linear time allocation. We can do better than that. But the concepts of splitting and boundary tag coalescing are general to all allocators, and that's why we cover this to begin with. It's nice and simple to understand, and it introduces us to those important concepts that the more complicated methods still use. Finally, as you walk away from this video as a whole, remember this is part 1 of Module 4. Part 2 will be in our next and final video for the module, and that's where we'll handle the other types of free lists. But we want to be able to describe the stack and the heap, what's the difference and how do they relate to each other and what are they used for. Describe implicit free lists. Let's be sure that we understand the difference between internal and external fragmentation and make sure that we can describe what coalescing is and how that works.